I'm going to be talking today about something we've introduced which we call PRIAS, which is the Pattern Region of Interest Analysis System. So, generally when we think of looking at a microstructure for EBSD analysis, we want to pick the right area. And, you can see from just the secondary electron and backscatter electron image, we can see grain contrast when we look at it flat with SEM detectors. But when we tilt for EBSD and we polish it really nicely, the efficiency of those detectors go down. We lose contrast in the signals. And so that makes sense. If you think about how things are arranged, when we've tilted the sample, we're tilting away from the regular imaging detectors. Your SE and your BSE are sort of optimized for a flat sample. And so when we've tilted the sample to 70 degrees, which increases our backscattered yield out towards our EBSD detector, we've positioned our EBSD detector in space to try to optimize that collection. That's why we've put it there. And so generally the solution has been, if we want to image for a tilted sample, you'd put a forward scatter detector somewhere around the perimeter of the phosphor screen. So the thing to remember is it was put there not because it's the optimal position for a forward scatter detector, it's the area that was available without blocking your phosphor screen, which was the primary emphasis of the system. And so if we look at the phosphor screen, you get more signal towards the center of the screen than you do around the perimeter. What's interesting is that as we look at the EBSD signal, we know there's a lot of information there. And the diffraction signal we extract via analyzing the lines and the Kikuchi lines and use that to determine the orientation. But we also know there's a great deal more information that's available from that signal that tells us stuff about the position, the current, the atomic number of the material, the surface condition, the topography, that is also being conveyed via that scattered signal rather than a diffracted signal. So the question we had going into this is that with all this information that's on there, we capture a small part of it via EBSD pattern indexing and forward scatter detector. Is there a way we can use our optimally placed EBSD detector to try to extract some of this other type of useful information? So what we came up with was a long convoluted process. And we started looking at, when we look at the signal on the phosphor screen, can we analyze it different ways? And so we implemented lots of different approaches of trying to quantify the signal that we were detecting. And you can see here, we got all sorts of different contrasts from different approaches. But really the key thing we saw was that with detectors, small changes in orientation could lead to large changes in imaging contrast. And so as we got down to trying to understand that, it led us to this approach that we eventually called Pattern Region of Interest. And the idea was, if we take our image of the phosphor screen, we can break it into an array of virtual apertures or regions of interest. And really what we're doing is we're going to monitor the intensity of the signal in each one of those regions of interest. So then as we raster the beam across the sample, we can use each one of these as an imaging detector and use that to reconstruct an electron image based on the incident electron flux for each region. And so what we get when we do this is this grid, this array of different images. So each image here corresponds to a different detector from that area. And so essentially you can think of this as 25 different virtual detectors from the phosphor screen. And what happens is each image generates a slightly different contrast. And the idea, if there's a strong pole centered in one of those ROIs, the intensity, the brightness is high. And then if it rotates or changes orientation so that pole skips to the next ROI, the signal drops in the first one and goes up in the second one. So if that pole is right on the edge of the ROI, a small rotation would be a large contrast jump. That's great, kind of like what we see with a forward scatter detector, but when we have all these, we're able to sort of track multiple changes so that between this whole set of images, we're able to see optimal contrast basically throughout the microstructure and see when things change. And of course the idea is that contrast and change is information when we're talking about imaging. And so this is, I guess there's a couple of interesting things to point out. If you look at this top left signal, in this case you don't see much change at all. And in all these, we're only clipping these a little bit. You can see in here how we get really strong contrast and it kind of changes modes. depending on the type of sample, this is now a multi-phase sample, there are times we get really strong signal contrast, even from those small little clips of the phosphor screen. And so we'll talk a little bit about the different kinds that we get out and how we can really, the way I've seen it is what you want to get is get all these images and then see is there a way to isolate and find the specific contrast you're interested in to show whatever you want to try to show. When we did this, really what we tried to do is to say, we can save the patterns and do this analysis, and we do that, but we wanted to use it as an imaging tool. And so we looked and said, what's required to use this as an imaging tool? The first thing is we need a camera that can go fast enough. We're collecting essentially at least a pseudo EBSD pattern at each point, so the faster we can collect it, the faster we can use it as a detector rather than just a camera. And so that's one area we wanted to work on. You need a phosphor screen that the decay time of the phosphor, how fast it goes from bright to dark, is small enough that we can scan fast. We don't want a latency problem as we move the beam. And so generally, older EBSD screens have had a screen that would limit us to about 600 frames per second. And so what we did is we found a better phosphor screen that allows us to go to much shorter decay times and makes this a viable type of an imaging approach with decay times in the microsecond range. And then, so we've named this called a PRIAS Live, again, kind of a live imaging, where we can collect these images at about 1700 frames per second. So it starts to be quick. We collect all 25 of those images simultaneously. So, the joke is yeah, it may take us 30 seconds to collect an image, but if we take it, the time per image, all of a sudden it's a very fast technique. You have to get 25, but you end up with a suite of images you can really work with, and I'll show you some examples. Once you have these, then you're able to start trying to do kind of your old classic A plus B, A minus B, but in a much more expanded capability to try to work on these different contrasts. So in addition to this just imaging mode, there will be two other modes that I'll talk about, which are available for sort of post-processing correlation with your regular EBSD data. One is which we call PRIAS Collection. This happens behind the scenes. And basically, we've predefined 3 regions of interest that it monitors while you're doing your regular EBSD mapping, records those values into your OIM data sets. And I'll show you an example. The other is PRIAS Analysis. And this is if you were to save all the patterns at each point, you're able to go in and define regions of interest for the saved patterns. And you have a lot more flexibility of what size of an ROI or virtual aperture you want to do for the type of imaging. And I'll show you a couple of examples of that as well. So for PRIAS Live, this is just a little screenshot. You can see, the sort of the deformation contrast that's available. You can see you end up with this array where you're able to select images. You're doing weighted processing. You can do grayscale or color or mixed. You have a nice little work area to work on it. Again, you can get a 256 by 200 image in about 30 seconds. One of the nice things is, if you think about just imaging in general, playing with your contrast and brightness, obviously you wouldn't want to do that with 25 different images. It sets all that up automatically through the smart team features. If you're familiar with team, we're able to do the color mixing, and then this data is accessible both in team while you're on the microscope and OIM analysis when you're off the microscope. So even if you've collected as an imaging, it flows with the data to be available throughout your whole workflow. So this is just an example, if you've seen team or not. The smart camera setup is basically a pull down in the workflow, where in this case it says PRIAS, the max speed. And so we have a couple of different speeds that you can define for PRIAS, and you just basically pull it down, say image the area. It sets up the camera to take advantage of it as an imaging tool rather than an EBSD detector, and collects the image. And I've put in here sort of the contrast of your brightness contrast sliders of forward scatter detector. When you're talking about just a single diode, it's okay, but if you're starting to talk about multiple detectors, it just becomes a little bit more cumbersome to have to optimize each one. And so this is just an example. This is a PRIAS Live image. This is a little bit higher resolution, 512 by 400, so instead of 30 seconds, it's 2 minutes. That's the type of general image we get from one of those ROIs. This is just to compare it kind of to an image quality map, where here we're talking 2 minutes, here we're talking 90 minutes. a lot of times we've seen people when they'll use some of their EBSD results, they're just putting up a map to show the microstructure. They're not doing any initial, quantitative measurements. They just want to see what's going on. You can see, yeah, that kind of communicates the same information very quickly in a short amount of time. So maybe now, is that really the area I want to do my full work on? And to show a couple of others, and with that same data set, I can now go in and say, here's an ROI. I always want to call it quadrant, just out of SEM term, but it's clearly not a quadrant, but it's a 5x5-drant. And here we'll see orientation contrast and some topographical contrast from some grain boundary precipitates that are present. And so what I can do is, rather than have that, I can just select everything. And in that case, what I saw is that the orientation contrast was suppressed more. But we start to see this atomic number contrast. This precipitate here becomes brighter in that image. And taking that to the next level, I kind of came up with a little recipe to say, well, let's do a couple of pluses, a couple of minuses. In that case, the grain boundary topography was suppressed, and it went more to just pure orientation contrast. And then I could go and say, well, let's assign some colors to those as well, and you get a nice colored microstructure where you see grain size and grain morphology easily. And so this is just an example from a dual-phase titanium sample where we've just selected 3 channels for RGB coloring and then 2 for grayscale. So we can combine the grayscale and color imaging, similar to what we do with just EBSD maps. Why do we do RGB coloring? It looks nice. It's a nice, pretty micrograph that communicates the structure. There's no quantitative link to the orientations. Generally, if you're familiar with EBSD maps, you might know that, okay, red might mean a particular orientation. That doesn't happen. One color here and another color here, they could be the same orientation, they could be different. There's no one-to-one correlation, which is a little different than general orientation imaging. But for just showing the structure, we found it's pretty useful. This is just an example. Another contrast mechanism we get is topographical contrast. So this is a rhenium alloy with a little tungsten alloying, where you can see distinct ridges on the sample, and you can see as I go from one side to the other, how that contrast changes across the ridges based on where are we getting a lot of signal, where are we getting a less. So by comparing one side to the other, you can really see topographical changes in the material. And then we can see atomic number contrast. So this is a PRIAS grayscale image showing the atomic number contrast versus a phase map. We see, yeah, there's some nice correlation between the two. Very similar to what you'd sort of expect from general backscatter type imaging. But we're able to feel like we can isolate those contrast mechanisms pretty easily. So this is just, again, this is sort of a backscattered image of a zircon. This is the same zircon imaged with PRIAS, and you can see if I toggle back and forth, the similarity between the two here, and then as it steps down, how we see the contrast change through that range. And we have all those collected simultaneously, so you're able to basically just do what I've done here is interactively say which one shows what I want to show the best. One of the interesting potential applications is that because we're not worried about using it as an EBSD detector, there's a lot more freedom of being able to run at different operating conditions without worrying about optimizing the band detection that we would for EBSD. So in this one, it was just taking a material, running it at lower kV to get, again, a phase map, and those are the chemical maps to say, look at how the phase contrast maps even at lower voltage. So it's, as we change the voltage, the scattering changes, we have all those ROIs so we can make sure we get the correct virtual aperture for the type of contrast we want to look for. And that's just showing 2 grayscale ones to show the correlation. So that's PRIAS Live. That's kind of the first third of information where it can be used as just an imaging technique. We don't have to do any EBSD mapping. This is a mode where we do that 3 predefined ROIs. The signal saved. Basically, the correlation with this is that when you've measured this, you're measuring the orientation, the chemistry, and the phase at the same point as well. So you're able to correlate whatever we see here with quantifiable microstructure. So, if you find that something in the PRIAS corresponds to something in material, that's going to be a link that lets us say, hey, maybe we don't need to do all the measurements later on. Maybe we can just look for a PRIAS Live image at that point. This is just an interesting example because, one of the things that happens is it happens behind the scenes. You don't have to set this one up at all. It just happens. So this was a sample we were looking at, and it was a colleague of mine, and this is kind of what we get from our general EBSD mapping. Our traditional is that we kind of get our SEM image here and our image quality map. Those are two general outputs. And the question he had is, he said, you know, I'm trying to find the interface layer. It's obviously a cross section. He said, I'm trying to find these little interface layers. There's multi-phase stack of materials. You know, I'm not getting patterns everywhere. He said, but I'm trying to resolve it. You know, have any ideas? And I said, well, did you try PRIAS? And his reaction, well, what's that? I said, well, you know, well, what version did you use? And he pulled up and said, well, you're lucky, it's already in there. He didn't have to do anything to set it up. I said, well, here are your maps. And you can see immediately that all these layers jump out. And you know, you can see this really tiny layer here. You can see the detail, the different phase contrasts that jump out compared to the earlier images. And it was immediately like, yeah, that shows exactly what I want to show. I was like, well, there you go. And so that's one application. Here is the other, you know, this is the sort of classical one, is that from those different predefined areas, from the same sample, we get your topographical contrast. You see the grains there for the orientation contrast, and then you see the phase contrast from the top strip. And the next slide shows a little bit better what I mean by that. Here are two different EDS maps. You can see how the hot spots here correspond with the contrast changes. You know, there's not a large atomic number difference, but we're seeing some good correlation between the two. And then the third is what we call PRIAS analysis, and this requires you to save all the EBSD patterns. This happens in Team very easily, and it manages all that. You're able to do some, you know, additional background corrections if you want, some pattern averaging if you want. Again, direct correlation with your measured EBSD results. Really, the key point from a PRIAS analysis point of view is that we can flexibly position and size those regions of interest. So I've drawn, you can see the one that's filled in, that's the active one. I've drawn a few different aspect ratios, a few different areas. You can draw them, you can move them around. Once you have them, you can do that same arithmetic, you know, addition, subtraction, weighted for these freely defined regions as well. And so the idea with this is that we can do a little more flexible imaging. So this is a standard forward scatter detector image of a deformed material. This is the general PRIAS analysis image that we've selected the bottom to sort of replicate what we'd expect for that FSD image. And then with the PRIAS analysis, selected a smaller region within the center, a much smaller virtual aperture. And we did that, we see higher contrast than we got with the earlier one. So we're just seeing smaller shifts that result in higher contrast.
Were you just looking for the poles?
In this case, it was just random. We just picked an area. You know, that leads to a great question of, you know, when it's textured and you know sort of what orientations are of interest, you can be much more selective of where, you know where your poles are, you can put those ROIs there and look for small shifts from a known orientation. So the more textured it is, the more you can glean from that. So this is kind of the fun application of this approach. This is your general forward scatter detector image of a nickel film. So you can see some topographical information in there combined with your orientation contrast. And so that's, you know, a lot of times with your imaging, you see multiple contrast mechanisms. When we tried the different regions, we still saw the same thing: orientation contrast plus changing topographical contrast. So what we wanted to do is to say, can we just get the orientation contrast? So we selected just a thin strip down the middle, and you see we get a map with just the orientation contrast, and the topographical data was suppressed. So all right, we can mix and match and get the information that we want and put away what we don't want to show. This is just a comparison of all three modes. You know, the thing to remember with both collection and PRIAS analysis, it doesn't come with a time penalty. You know, it just runs. You don't have to worry that it's going to make you run slower. PRIAS Live, we get in about 2 minutes. Those two maps are about 15 minutes. And the good thing is you see there's good correlation between this and this. This is looking at it in colored space. Again, that provides a nice, just colored microstructural image in 2 minutes. The one on the right gives us more flexible correlations with orientation if you do have specific things of interest. This is the one, so the map on the right is a standard, what we call a grain map. So we've gone through, we've analyzed the orientations, we figured out what grains are present, and then randomly colored it to show what the morphology and grain size is. The one on the left is just PRIAS colored maps, and you can see they both give an idea of what the shape and size of the grains are. You get a good first order look at the microstructure. that's kind of the imaging approach. And then the next step is to say, can we do more analytical imaging with this data? So here again, we have these 5x5 array of different signals. What we want to do is to say, can we tell between all of those when the pattern changes? You know, and not just change from one to the other. You know, when does something change significantly that we'd say it's one orientation or the other, whatever our criteria is. So we have an approach where we do kind of a vector comparison, and these kind of show the results of the white lines show essentially where the grain boundaries are on the two maps on the left, versus one on the right where we have the grain boundaries shown with orientations. And you can see hopefully that there's really good correlation, that now we're able to actually find the position of the grain boundary. We can define the grains without actually having to map the whole thing. So we can find grain positions in, you know, a 30-second to 2-minute map rather than a 90-minute OIM map. So we can get some good quick information that can lead to some other smarter approaches for sampling the data if you wanted to. This goes back to your comment, Kathy, of, you know, when we do the RGB coloring, though, remember that the colors don't correspond to orientations. And in this case, this film is actually very strongly textured. It's 1-1-1. So here's the variation in color isn't really showing the variation in crystal orientation. So if you're used to OIM maps, you have to be a little careful how you initially interpret it. It's counterintuitive of what it's showing you in that regard. And then this data, I mentioned, it's put into the data file and can be transferred into OIM analysis. So if you're familiar with that approach, is you can bring in this is a chart. We're doing some highlighting. We're showing the grains that have a certain PRIAS value. We can do it from any of the quadrants, and it funnels right into that analytical approach of highlighting and partitioning and subsetting. So it adds more information channels to an already large toolbox available to help understand your microstructure. And then the other cool thing is, as sort of a complementary technique, is that in the last few years there's been something which is called transmission EBSD, which is instead of doing backscattering, we use an electron transparent sample. The beam goes through it. Because of the thinner volume, you get a higher spatial resolution, with the advantage of you're using the same detector. And so this is a transmission FSD image. Again, the same advantages we see before. By using the PRIAS approach, we get a number of different t-FSD-ish type images. And if we compare it to the image quality map, you can see we get more data in this case through a foil where the thickness is varying. It's a TM foil with variable thickness. We're able to get more contrast as we get thicker, whereas with the image quality map, band detection had failed a little bit earlier. And so this is just a colored t-EBSD map where you can see, you know, we're getting data all through that little section where we can't really get EBSD information, but we can get microstructural information. This is just a little selection going through the foil, and you're able to see, you know, it's almost like you're playing with contouring of how you click it, and you're seeing different areas where the contrast is highlighted. In summary, you know, again, we call it a new imaging approach or technique that, you know, we use the EBSD detector both as an EBSD detector as well as an imaging detector. So hence the hybrid. The three modes of operation, there's the PRIAS Live, which is imaging, PRIAS Collection, which is just behind the scenes happening, and PRIAS Analysis based on safe patterns, where we can define specific ROIs, enhance, suppress, and isolate and select the contrast of interest, and correlate that with orientation data as well.